So let's start the semiconductor devices now. This is our lecture 1. We will be starting from very scratch. We will be having no gap in our understanding. Now, when we talk about the semiconductor devices, let's first talk about the semiconductor. Because the semiconductors have very few free electrons in them, the conductivity of the semiconductor is between the conductors and the insulators. Now, where from these free electrons comes up? What is the nature of these free electrons? In order to know this fact, we need to find out the atomic structure. We need to know about the atomic structure. That means the structure of an atom. When we are discussing about the atomic structure, we do not discuss the atomic structure in terms of the position of an electron into the atom. We often do talk about the atomic structure in terms of the energies of the electrons which electrons can take up in an atom. So now here we are talking about a single atom, and we will be discussing the energies of the electrons in a single atom. Then from there on we will be moving to the solids which are made up of large number of atoms. So what will be the effect of large number of atoms when we bring up those large number of atoms together? We will be discussing these facts later, but let's talk about the single atomic structure and the atomic structure in terms of the energies of an electron. So according to quantum mechanics, an electron can take up, let me write it, electron can take up only discrete value of energies. Discrete values of energies, okay? So electron can take up only the specific values of energy. It's like a digital signal, okay? So electrons cannot take up all the energies. Now let's see the diagram. So I have drawn the different energy levels here. So this axis is energy, and let's say this is our ground level of energy, okay? This is the first level of energy which the electron can take up. Similarly, this is the second level, and let's say this is the third, this is fourth, and this is the fifth energy level. Now in between these levels there cannot be any electron, okay? So there is no position of electron in between these levels, okay? So electrons can take up only these energy values. Let's say this is E1, this is E2, E3, E4 and E5. So either electron can take up E1, E2, E3, E4 or E5. In between E4 and E5 or in between these any two levels there cannot be any electron, okay? Now that is fine. Now when we are talking about, let's say, the silicon atom, the silicon has the 14 electrons, yes? Now how these 14 electrons are going to fill up these energy levels? Now these electrons fills up these energy levels according to some rules. It is not that randomly we can put up any electrons in any of these energy levels. First of all, the fact is that any electron wants to go into the lower state of the energy, okay? This is the number one fact. And there is a rule, or which we also call the Pauli's exclusion principle. Pauli's exclusion principle states that there cannot be any two electrons which can occupy the same quantum state, okay? So now we are discussing that how these 14 electrons or whatever number of electrons are there, how these electrons will be going, or how these electrons will be filling up these energy levels, okay? So for that we are discussing some few facts. Now number one rule is there is no two electrons which can occupy the same quantum state, okay? Now what is the quantum state? So quantum state is a particular state of an electron described by the set of quantum numbers. Okay, but what are the quantum numbers? So there are 4 quantum numbers which I have written down here for you just to save the time. So there are 4 quantum numbers. So the first quantum number, which we call a principal quantum number, which is denoted by this n, and this is principal quantum number which also describes the main energy level of an electron. Now the value of n can be any positive integer starting from 1 to any positive value. There is a second quantum number which we call angular momentum quantum number, which we denote it by L. Now the value of L can be from 0 to n minus 1. So for example, if n is equal to 1, the L value can be only 0 because n minus 1 is 0. Okay, so for n is equal to 2, L can be 0 and 1. Yes, because the n minus 1 is 1. So in this way, n and L are defined. Now, one thing, L is equal to 0, is also described as S orbital. Okay, and L is equal to 1, we also describe it as p orbital. Okay, so these are the orbitals. For the L is equal to 2, let me write it. For L is equal to 2, we describe it as d orbital. Okay, and similarly for L is equal to 3, we call it f orbital. Okay, so in this manner it keeps on going. Okay, now the third quantum number is the magnetic quantum number, which we denote it by m's of L because the m is dependent on the L. The value of the magnetic quantum number is from minus L to plus L. Okay, so for example, let's say n is equal to 2. Okay, for n is equal to 2, we saw L can be 0, or L can be 1. Yes, and for 0, L is equal to 0, the m's of L would be 0 only because minus L or plus L is 0 only. There cannot be minus 0. And for L is equal to 1, m's of L can be minus 1 to plus 1. So minus 1, 0 and plus 1. Yes. So in this manner, the ML will be defined. Now the fourth quantum number, which we call it as spin quantum number, which is denoted by S. Now this spin quantum number describes the spin of electron around an axis. So it can be plus half or minus half. Okay, so it can be rotating, electron can be rotating in this direction or in this direction around an axis. Now we will not be going into the much deep details here because which is not relevant for us, but what I want to tell you that these are the 4 quantum numbers defined for an electron. Now let's go back to the definition of quantum state. Quantum state is described by a set of quantum numbers. Okay, so if you take any set of these quantum numbers as N, L, m's of L and S, if you take any set, we call it a quantum state. So now let's take an example. Let's say we are having, for n is equal to 1, we defined for n is equal to 1 L is equal to 0, yes, and amps of L would be 0 also, and S can be plus minus 1/2, yes, and L is equal to 0, we called this L is equal to 0 as S orbital. Okay, now let's take another example. For n is equal to 2, we can get L is equal to 0 and 1, yes, and for L is equal to 0, the amps of L would be 0 and S would be plus minus 1/2. For L is equal to 1, ML can be minus 1, 0, plus 1, and S would be, for each amps of L, S can be plus minus 1/2. L is equal to 0, we call it as S orbital, yes, and L is equal to 1, we called it P orbital. Okay, so now what I want to tell you, if you take any particular set, let's say for n is equal to take n is equal to 2, how many sets are possible? So n is equal to 2, and so n is equal to 2, L can be 0, and then from L is equal to 0, ML can be 0, and S can be plus minus half, yes, plus half. So another set can be 0, 0, 0, minus half, yes. Similarly, for L is equal to 1, the n is equal to 2, so 2, then L is equal to 1, so I am writing it as n, L, amps of L, and then S. Okay, so it can be 2, 1, then amps of L can be minus 1, S can be 1/2. Okay, so in this manner there are many possible sets. Now each set is defined as quantum state. Okay, quantum state. Now let's go back to, so the for n is equal to 2, how many quantum states are defined? How many quantum states can be there? So n is equal to 2, L can be 0 and 1, yes, so we define it as either 2 of S or 2 of P, yes, and for 2 of S there can be only 2 electrons because S can be only plus minus 1/2, and for 2p, that means for L is equal to 1 and n is equal to 2, there can be 6 electrons, okay, or the 6 quantum states, because for each amps of L there can be 2 values of S. So for 3 values of amps of L there can be 6 states, yes, 6 possible combinations can be there for n is equal to 2 and L is equal to 1. And for n is equal to 2, L is equal to 0, only the 2 states would be there because amps of L is 0, so S can be plus minus 1/2. So 2, 0, 1/2 and 2, 0, minus 1/2, only 2 possible sets would be there. So each possible set is defined as the quantum state, just I want to tell you. Okay, so now, okay, these two things we have discussed. First is the Pauli's exclusion principle, which says that no two electrons can occupy the same quantum state, and then we have discussed about what is quantum state. Now let's fill up these energy levels for an silicon. Okay, so the first electron, so now let me remove this. So we also call these energy levels as 1s, 2s, 2p, 3s, and 3p. Okay, so this is same as n is equal to 1 and L is equal to 0. Yes, this can be n is equal to 2, L is equal to 0. This is correspondingly n is equal to 2 and L is from minus, so L can be 0 or 1. Okay, so 0 or 1. Okay, similarly, so now these energy levels are also defined as 1s, 2s, 2p, 3s, 3p. Now how the electrons will be filling up these energy levels? So the first electrons, now the fact I told you that electrons wants to go into the lowest state of the energy. So let's say in the 1s we saw that there can be 2 electrons. Okay, so for n is equal to 1 and l is equal to 0, s can be plus minus 1 by 2. Yes, and amps of l is equal to 0. So for this 1s there can be only 2 quantum states. Yes, so for 1s, and this fact is also consistent with the Pauli's exclusion rule, because in the 1s energy level there are 2 quantum states. So there can be 2 possible electrons in the first energy level, which is 1s. Okay, because there are 2 quantum states available at this energy level. Now similarly for the 2s there would be 2 quantum states, so there can be 2 electrons. Yes, similarly for the 2p there are 6 quantum states, so in the p there are 6 quantum states. Yes, so because there are 2 values of l, okay, forget about l because l is considered in the p. There are 3 values of m, and each m can have the value of s as plus half or minus half. So 3 into 2 would be 6 quantum states. Okay, so in the 2p there would be 6 quantum states, so there can be 6 electrons in the 2p. Similarly in the 3s there can be only 2 quantum states, and in the 3p there would be 6 quantum states available, but we are only having remaining 2 electrons, because 2 and 2 and 6 and 2, and then these 4 states would be empty. Okay, these are 4 empty states. So there are possible 6 quantum states available, but we only have the 2 electrons available, so these 2 electrons will be filling up this energy level 3p in the last. Okay, so this is how the energy levels are going to be filled by an atom. Now this is about a single atom. Now later in the video we will be talking about when we bring up the large number of atoms together and the inter-atomic force starts to play. Okay, so these energy levels, these are the energy levels. Okay, these energy levels will be splitting up into the energy bands when we will be bringing the large number of atoms. So this we will be discussing in the next video.